thank you. Thanks for inviting me here to speak. Can everyone hear me okay? It's good? Okay, fantastic. Yeah, so I'm going to be talking about higher form symmetries in AdS CFT. The subject is, in terms of dimensionality, is general, but I'll try and keep the examples and things to AdS 3 because that's the point of why we're all here. Most of what I'll say can be found in this paper from late last year, and then there's some work in progress that I will comment on as I go along. So the name of the game here is to try to reproduce universal features of holographic CFTs. So if you were to take gravity in AdS spacetime and use the AdS CFT dictionary to calculate various properties of the CFT, you would find that they're very special properties that, you know, some generic theory you might write down would not have. So the idea is to try and invert that, try and write down all the sorts of features that you would want a CFT to have so that it becomes effectively holographic. So it's equivalent to some gravitational theory in AdS spacetime. That's what I would like to talk about today. The main sort of tool I'll use throughout the talk is a symmetry called center symmetry, and I'll talk about it once we get there, and a mechanism that was written down about 30 years ago now called the Iguchi-Kawai mechanism, and I'll go over all of these in the introductory part of the talk. Then I'll go ahead and reproduce certain universal features of gravitational theories in AdS using this symmetry principle and this Iguchi-Kawai mechanism. And then I'll talk about various sort of offshoots, an extension of these symmetry principles and mechanism to curved backgrounds, and it's what it has to say about the Wald entropy, which is the entropy of black holes in general higher derivative theories of gravity. And the title of the talk was about higher form symmetry. So center symmetry is a one-form symmetry. In general, you can have p-form symmetries. I'll stick to center symmetry for most of the talk because that's the thing that is really well understood. But I'll talk about how the story is actually more general and is about higher form symmetries. And then I'll just talk about things to do from there. Okay, so what are the sort of universal features that one might be interested in? There's several things that we know from various examples. The most immediate one is large N, okay? Another one is that you want the CFT to be interacting. So let me specify a little bit. I'm in particular interested in local bulk theories. So I'll comment about higher spin examples, but they're sort of out of the purview. They don't have certain nice features that I would like to reproduce from the CFT point of view. Another thing is that the CFT is almost always some sort of gauge theory. Okay, this might be a little bit weird depending on your point of view because we're taught from our youth that being a gauge theory is not a physical thing. It's some redundancy of description. So you might ask, why is it that it's always gauge theories that are appearing? And I think this point of view will give one way to understand that. Again, that's not a physical problem. It's sort of a psychological or sociological problem. But it's an interesting thing to wonder about. I'm sorry?
In CFT2 in particular, that's one slightly sort of odd case where it's not obviously a gauge theory.
Well, it depends on what you mean. I think the CFT2 case can also be understood as a gauge theory. You mean in like the symmetric orbifold type of situation?
Well, yeah, so that's quite different than AdS.
It's different, but I still think it's some sort of gauge theory. I mean, the way you understand that is effectively like some sort of discrete gauge theory, I think. But yeah, I'll say a little bit more about that. But it is qualitatively different. I agree. Okay, a little bit more concretely. I mean, these three things are equivalent to one another. I'll get to it a little bit later. But the free energy of the theory, just the finite temperature partition function, is very special for holographic theories. It has some very simple form. It's related to the fact that you have a sparse spectrum of light states on a torus. If you're in 2D, if you're about CFT2, it's just a sparse spectrum of light states on a circle. And it's related to something that's been talked about for a while now, which is that the Cardy formula, which is some asymptotic formula for 2D CFTs, has some extended range of validity for holographic theories. It holds not only asymptotically, but up to some finite point. Another property is you want sort of parametrically large dimensions for higher spin single trace operators. This is sort of, decoupling stringy things in the bulk. This has been talked about a lot in 2D. You want small OP coefficients. Another thing which I'll comment about is the bulk point of view shows you that if you take a correlation function in some AdS background and consider a smooth quotient of that AdS background, then the new correlator can be constructed by a sum over images, basically because the theory in the bulk is free at large tooth coupling. And there are lots more. I just wanted to list some of them. I won't be really commenting on all of these. I'll be commenting on some of them. But it's a bit of a mess. There are lots of properties. The logical structure between them is not exactly clear. So you can ask, are there any sort of unifying principles for at least some of these features? And a natural sort of unifying principle, some sort of symmetry principle. And another thing is, how is this all related to the existence of strings and branes? I mean, some people at some point started saying things like holography is general and doesn't really need strings or branes in the bulk. It's just some statement about gravity or quantum gravity. From this point of view, we'll be able to actually connect to, not really in this sense, but it's very suggestive that you need some sort of non-local objects to get this, well, paradoxically, to get this kind of local gravitational theory in the bulk. So the proposal, it's in red, is that center symmetry and generally higher form symmetries in CFT are the symmetry principle, which lead to certain universal features that you would want. And they imply the existence of strings and branes in the bulk, or some sort of non-local objects. Okay? Good. So what's center symmetry? Let's do a quick review. It's a symmetry. I mean, it looks like a symmetry under gauge transformations, but your gauge transformations are twisted in a certain way. So the usual gauge transformations are you take a gauge field A mu, and you do this sort of transformation to it. So this parameter G is some map from the space-time of your theory. Here I've just parameterized it as some generic D minus one dimensional manifold times a circle into the gauge group. I'll stick to SUN basically throughout the talk, but this is general. And for it to be a gauge transformation, usually, well, not usually, we require the parameter G to be periodic as you go around this circle. Okay, so usually this H that I've written here is not here, and that's a gauge transformation. You can twist it, though, by this element H, which is an element of the center of the gauge group, and that's a center symmetry transformation. Okay, so for example, pure Yang-Mills has this as a symmetry. This is a global symmetry now. It's physical. Okay, it's not any sort of redundancy of description. So it's a symmetry of pure Yang-Mills. It's broken by matter depending on what representation it's in. For example, fundamental matter breaks the symmetry. We don't really need to talk about that too much. And you can ask, what sorts of things transform? What are the order parameters for this symmetry? Like I said before, center symmetry is a one-form symmetry. So its order parameter is not going to be some sort of local operator. Now it's going to be some higher dimension operator. In particular, it's going to be a loop operator. So the Polyakov loop, which is a Wilson loop that wraps this S1. If you take it in the fundamental representation, then it transforms by this element H. H, remember, is some arbitrary element in Zn. Okay? Good. But what that means is its expectation value is an order parameter for the symmetry. And physically, it's related to the confinement-deconfinement transition. I won't really get into that, at least at finite temperature, it's related to that. So that's the lightning review of center symmetry. Any questions about that?
Sometimes we think about the gauge theory as just a random field, not having gauge group SUN, but having SUN sort of modded out by Zn.
Yeah.
If we don't think of it that way, then we would think of roughly super selection sectors instead, where you would have some operator or something which carries this discrete charge, and you expand around that operator.
Yeah.
Is that roughly what you're
Sorry. Well, I'm never going to quote. I mean, you can talk about SUN mod Zn. I'm never going to do that. I'm always going to stick with SUN. There you have to be a little bit more careful. For example, it's not there. It's a little bit confusing how Wilson loops, which aren't really good loops in that case, or order parameters. You can still talk about this stuff, but I'm not going to comment on that case. It's a very interesting case. I'm happy to talk about it later, but I won't be talking about that. I just want to do the simplest case for now. Okay. There's another nice feature about these Wilson loops that in gauge gravity duality, there's a simple way to calculate them, at least in the semi-classical limit. You basically take a classical string world sheet in the bulk that ends on this contour C at infinity. In this case, C is just we're wrapping the S1. So it's a circle at infinity, and you effectively calculate the area of this world sheet. So that's really annoying. One quick thing that comes out of this prescription is that if your circle at infinity is not contractible in the bulk, then the expectation value is 0. Okay? That's really all we need to know about this prescription. The one other thing, and this is really an assumption, but I'll motivate it, is if we want a smooth gravitational description, which is not necessary in holography. I mean, you can have sort of singular spacetimes that you really need string theory to understand, but I'm just going to, by fiat, restrict myself to cases that are described by just the supergravity approximation. To maintain smooth gravitational description, you can only have, if you have several circles at infinity, you can only really have one of them cap off in the bulk. Okay? You can't have, at least in a translation invariant state, you can't have two of them cap off in the bulk without having some sort of conical singularity. Okay? But what that means is that center symmetry is preserved along all of the cycles except for one, the one that caps off. So remember, if it's not contractible, this is 0, so center symmetry is preserved. And so the one cycle that caps off is the one that breaks center symmetry. So it will become pretty concrete. Well, not right now, but in a second we'll become concrete about this in a simple example that everyone knows. But let's do the last part of the introduction. So this first paragraph is really describing the Gucci-Kawai mechanism. It's really basically a theorem, okay? It says that if you have a large n center symmetric gauge theory on some, again, manifold that parameterized arbitrarily as some md minus n times a torus, an n torus, then if you preserve translation symmetry and center symmetry along a given circle in the torus, then appropriate observables, I'll define appropriate as we go along, but it's understood what observables are appropriate. They're independent of the size of the circle at leading order in n. Okay? This is just a fact. As argued originally by Gucci and Kawai in the 80s, and these three authors with combinations of other people have improved upon this a lot in recent years. It's also known as large n volume independence. People refer to it in different ways. And a lot of the story historically was, right, so preserving center symmetry. So if you break center symmetry, I said that it's a good order parameter for confinement, deconfinement. And we know that gauge theories in general at high temperature deconfine, or are deconfined. So generically, if you take the circle size small, you'll break center symmetry. And a lot of the work in the 80s and 90s was to try and prevent this transition from occurring. So people tried various things. They wrote down different models. So pure Yang-Mills, that was the case that Gucci and Kawai were interested in. That thing deconfined, so the center symmetry breaks. People wrote down different models, twisted Gucci, Kawai, quenched Gucci, Kawai, they had all sorts of funny names to try and prevent the deconfinement transition from happening. Okay? I'll just point out one case, which is what these authors wrote down, which is an interesting theory called, well, QCD. It's QCD, but instead of having fundamental quarks, you have adjoint quarks. So your matter is in the adjoint. This thing preserves center symmetry at the Lagrangian level. And if you give the fermions some sort of specific periodicity conditions around the circle, if you make them periodic, then you prevent the deconfinement transition from happening. So it's center symmetric for all circle sizes. And this, for example, has a very quick and simple gravity dual. If you give fermions periodic boundary conditions around a circle, then that circle cannot cap off in the bulk, because that's an inconsistent spin structure. So that's sort of the first connection we'll see between these Iguchi-Kawai type ideas and gravity. Let me rephrase something I had on the previous slide. We're going to assume, again, by fiat, a smooth gravitational description. When we talk about universality and gravity, that's really what we're talking about. This means, by this theorem, that appropriate observables are going to be independent of the size of all of the circles except for one of them, the one that caps off in the bulk. Now, which one caps off can change as you vary the circle sizes, right? As we know, you have basic deconfinement transitions like thermal AdS to BTZ, where you go from the spatial circle capping off to the thermal circle capping off. So which one caps off can change, but you can only ever have one of them cap off. Okay. And the punchline, if you're tired and want to go to sleep, is that this Iguchi-Kawai mechanism theorem, or also known as large n volume independence, it precisely mimics weakly coupled field theory on gravitational backgrounds. So the things you get just by calculating free fields in in gravity and translating into field theory language, into a holographic field theory language. If you wanted to invert that, you would get it by taking a field theory and being in this regime where you have large n volume independence. So that's the punchline. And let's do a few basic calculations to make this concrete. So I said that appropriate observables are independent of the size of the S1. So the free energy density is one appropriate observable. Okay, so that's a very concrete thing we can calculate. And we can in particular consider AdS3 CFT2. I told you my examples would be in that context. We can consider the transition from thermal AdS3 to BTZ. So as you increase the temperature and beta becomes of order L and smaller, you go from thermal AdS dominating to BTZ dominating. Okay? So in thermal AdS, it's the spatial circle that caps off in the bulk. So the field theory lives on some torus, and the AdS3 geometry just picks a cycle that caps off in the bulk. So turns it into a donut. And so the expectation value of the Polyakov loop around the thermal circle is 0. So center symmetry is preserved here and broken here. What would the Iguchi-Kawai mechanism tell you? It would tell you that the free energy density had better be independent of beta, the size of the thermal circle. And indeed, if you calculate it, it is. It goes as 1 over L squared. I haven't tracked the numerical coefficient. It's not important. But it does not depend on beta. Okay? In the BTZ case, the roles just reverse. Now you break center symmetry along the thermal circle. That means you're deconfined. You preserve it along the spatial circle, and the free energy density is now independent of L, the size of the spatial circle. So this very basic thing passes the test. And you could, in fact, determine all of this. So I just gave you what, the answers that gravity spits out at you. But the whole point is to forget about gravity, start from CFT, and try and reproduce the gravitational results. So if you did that, if you use the assumption that I said, which is that center is preserved along only one cycle, if you couple that with modular scale invariance, this will completely determine the free energy for you. It'll determine it to be this, as long as beta is greater than L, and then a sharp transition to this as long as beta is less than L. Okay? And this actually implies, once you get that, this implies other things that people talk about. For example, the extended range of validity of the Cardy formula. So here's the Cardy formula. In general 2D CFT, it's an asymptotic formula, meaning it's true as E goes to infinity. But in holographic CFTs, it's actually true for all energies greater than C over, okay? And reproducing this free energy in the way that I said actually implies this by just some basic large N thermodynamics. The canonical and microcanonical ensembles are equivalent, so you could translate statements about the free energy density or the entropy density into statements about this, this microcanonical density of states. So okay, that comes out. And it also immediately implies a sparse spectrum of light states. Light means E is less than C over 12, and you get this bound. As you can see, it's not incredibly sparse. This is sort of a Hagedorn type scaling, but it gives you that. And these authors talked about the relation between these ideas. Not in the central symmetry context, just the relation between having a universal free energy, having this type of extended Cardy formula, and having a sparse spectrum of light states. Okay? And you can generalize this argument. As people may know, for if you're doing Euclidean gravity, there's actually some SL2Z family of black holes. It's not just these. And you could extend these sort of central symmetry type arguments to get the free energy, to get the sort of richer SL2Z phase structure. And you could also extend it to higher dimensions, which I won't talk about because I promised to stick to AdS3. So any questions about that? That's the first basic calculation. Yeah? Yeah, so let's say we take a higher dimensional theory, a higher dimensional CFT on a torus, a d-dimensional torus. The assumption was, again, that only one of them ever caps off in the bulk. And so you get independence of the free energy density on all but one of the cycles. And since it's scale invariant, that basically fixes it exactly up to some number. And then you can also make arguments about that number. So it's, in fact, it's more powerful in higher dimensions because in two-dimensional CFT, we already know, for example, the thermal AdS3 phase is where the theory is basically dominated by the vacuum, and we already know how the vacuum energy scales just by scale invariance. In higher dimensions on a torus, we don't know how the vacuum energy scales. It could be a complicated function of the moduli of the torus, but the center symmetry assumption gets rid of all that dependence and gives you some universal functional form. So it's even more of a tool in higher dimensions. Okay. So, you know, the free density is nice, but it's a 0-point function. It's not the most interesting thing in the world. You'd want to say something about correlators. So let's go back to just having a single circle in our field theory and consider some local operator O. You can make some statements about non-local operators, but I'll stick to local ones. And just decompose it into Fourier modes with momentum P. So appropriate observables in this context are I'm sorry? Yeah, everything I'm saying in this talk is the leading order and so, yeah, that's right. Yes?
So this expectation value of W, which you had in the previous slide, so that is based on universal features, like, or you showed that it's equal to 0 and not equal to 0, and does it take some specific value depending on the single charge or?
Yeah, all I really care about is when it's equal to 0. I don't care about what it's equal to when it's not equal to 0. I just care about whether symmetry is preserved or broken. But gravity gives you a particular answer for when it's not equal to 0. I'm sorry?
It should be proportional to, it should live in Cn, doubling the expectation.
Oh, yeah. Okay, so the statement, the appropriate observables in the case of correlation functions is you don't really want to think about these O of x's. You want to think about correlators of these O of p's. And if you consider a box, a circle of size L versus a circle of size KL, where K is some positive integer, then the correlators that are independent of K in this case, that's the discrete change you're thinking about, are ones where the frequencies are commensurate in the two sizes. So that's a little bit annoying. It implies something very concrete about position space correlators. What it implies is consider a 2-point function and the circle is of size L. It implies that it's given by the 2-point function of infinite size by this equation, which is really just the sum over images of the infinite size 2-point function. Okay? And this should look familiar for people who've done, you know, basic AdS 3 calculations. If you consider the BTZ background and consider a 2-point function of some operator O in the bulk, it takes this form, where you now have a sum over images over the spatial direction. Now remember, the spatial direction is the center symmetry preserving direction, and so it's consistent with what Iguchi-Kawai exactly predicts that you should get this sort of answer, where it's a sum over images in the spatial direction, but not the time direction, because the center symmetry is broken there. There's no nice independence of that thermal circle. And there's a similar, you know, the thermal AdS answer is the same, where it's a sum over images of the thermal direction. From the bulk point of view, this is very simple to argue. Again, you have basically free fields in the bulk. So if you have some, you know, the CFT 2-point function is given by a bulk-to-bulk propagator, which you sort of extrapolate to the boundary and strip off some factors. The bulk-to-bulk propagator satisfies some Green's function equation. So if you do a quotient of the space-time, BTZ is a quotient of AdS, then the new Green's function is given by a sum over images. That's the bulk argument for why this happens. But there's an independent CFT way, if you assume the center symmetry, to get the same sort of behavior. And it's one of these nice universal features of holographic theories. There are other, okay, I can't call them observables, but there are other things that have nice volume-independent properties. The single interval entanglement entropy in the thermal AdS background or the BTZ background takes this form. So notice this answer doesn't depend on beta, and this answer doesn't depend on L. And, well, that's a little bit stronger than this, because this sort of is given by a sum over images. There's no sum here. And that's related to the fact that this entanglement can basically be calculated as a 2-point function of heavy operators. Heavy meaning not scaling with the central charge, but scaling large enough such that the geodesic approximation is a good one. But the point is that this property, which again is a special thing of holographic CFTs, is explained by this center symmetry principle. In general, for a 2D CFT on a torus, there would be beta dependence here. And for example, the Renyi entropies of holographic theories also have beta dependence here and L dependence here. But it's absent because of this symmetry. Okay, that was just 2-point functions. It's a similar story for multi-point functions. If you want to consider a Witten diagram, so this is AdS, this is the boundary CFT, and you want to consider some 1, 2, 3, 4, 5, 6, 7, 8, 9-point function. We want it to be tree level, okay, in the bulk. That's saying that you want the leading and end contribution to the 9-point function. Then that object also, from the bulk point of view, can be written as a sum over images because the atoms of this Witten diagram are bulk to bulk and bulk to boundary propagators. And again, these have this nice property that if you quotient the space-time, the new propagators are given by sums over images. So a generic m-point function is given by this. And this is exactly what Higuchi-Kawai would tell. If you just started from a field theory and said, I assume center symmetry is preserved along one of these circles, and I want some higher point function, it would spit out precisely this formula for what it is if you were to quotient the space-time. Now, what about loop diagrams? Like this guy. There's a loop here, okay? These guys don't have any nice sort of volume-independent property. The loop integral that you have to do messes that up. And that's, you know, consistent with Higuchi-Kawai because Higuchi-Kawai only makes statements about leading and end pieces of observables. Of course, all the atoms of this diagram are the same. This is still made up of bulk to bulk and bulk to boundary propagators. So at the level of the integrand, before you do the loop integrals, it has some nice volume-independent properties, but it doesn't really translate into the final integral. So sorry, this is not leading order and end. Yeah. Okay. So yeah, it's a Witten diagram. Sorry. Ooh. Sorry. Witten diagrams. Good. Okay. So those are the sorts of things you get. This nice sum over images. And let me emphasize, people often the sum over images that comes out of these bulk calculations, people often say a certain wrong thing about them, which is that this is just because large N theories are free. And in some sense that's true, but you know, it's free in a very particular sense. So as I said, it's a sum over images only along center symmetry preserving circles, not the other ones. So the generic freeness that large N theories give you is not sufficient to get it to be a sum over images. Okay? You really need this symmetry. Okay, any questions before I move on? It's going to get a little less concrete from here on out. Okay. 10 minutes, great. One thing you might ask is, you know, this volume dependence thing is nice, but really it only tells you about circles, those don't have any curvature. What if you consider your CFT on some actual curved background? In AdS CFT, we should be able to put our CFT on any background we want. Usually you'll put it on a sphere. In AdS3 CFT2, we're lucky, a sphere has no curvature, so it's all nice. But in higher dimensions, you know, can you say anything about putting the CFT on a spatial sphere? In other words, is there volume independence with respect to changing the size of the sphere? Some basic field theory intuition which suggests to you what should happen. The argument for this large N volume independence, well, I'll give you the argument. It's sort of not correct, but I'll give it to you because it helps thinking about it. The argument is if you're in a large N theory and you preserve center symmetry, let's say along a thermal circle, then you're in the confined phase of the theory. Okay? Your confined phase degrees of freedom at large N are things like mesons and glue balls. And these things in large N counting are weakly interacting with each other. They're effectively free. They basically interact at first subleading order in N. But what that means is that leading order in N, they don't know that they're in a box because they can't interact with their image. So that's why there's no real dependence on the size of the circle leading order in N. Okay, that intuition seems to suggest that it doesn't matter what kind of box it is, right? It could be a spherical box or any kind of box, but the problem is it can, you know, these confined phase degrees of freedom can still detect local curvature. If you change a sphere by changing the radius of the sphere, the confined phase degrees of freedom can know that because that's a local change that you're doing. However, if you change the size of the sphere sort of topologically doing some quotient, let's say you do a Z2 quotient, that it shouldn't know about because the local curvature is identical. It's some global thing that you changed. So that's what field theory suggests. And from the AdS CFT point of view, this is just totally obvious. If you just calculate some basic things, You could consider, you know, some spherical AdS Schwarzschild black hole. Now I really have to be in higher dimensions. Sorry, forget about BTZ. We know that the scaling of temperature with the horizon radius is something like this. What that means is the Bekenstein-Hawking entropy, which scales as the area of the horizon, cannot scale as temperature to the d minus 1 because of this. So if it doesn't scale like this, it means it doesn't scale like the volume. Okay? And scaling like the volume is what would have made the entropy density independent of the size of the sphere, and that doesn't happen. Okay? So not surprising again. It's only really sort of extensive scales with the volume at very high temperatures when you could ignore this factor, and then you're basically back in the black brane phase, and you can use these arguments. But under space-time quotients, totally trivial, if entropy goes as the area, then it changes to A prime, which is the area divided by however much you quotiented by. So that supports the fact that topological changes in volume do have nice sort of volume-independent properties. Okay? Good. But that last thing seems to suggest, you know, maybe this Iguchi-Kawai business or the center symmetry business might be able to sort of pinpoint or predict for you something like the Bekenstein-Hawking law, the fact that entropy scales with area. And that would be great to get something like that from the CFT point of view. So you can ask, does it do that? And the fact that there's a pause here should suggest that no, it doesn't quite do that, because there are a lot of, you know, functions you could write down that were you to do a quotient change by the amount you quotiented by. And what Iguchi-Kawai predicts is actually something about the walled entropy. So the walled entropy generically has this feature that if you were to take a quotient of the space-time, you reduce, you know, the area of the horizon by the amount you quotient by. That's effectively because the walled entropy is written as some local integral over the horizon. Okay, that's a special property. It didn't have to be that way. It didn't have to be that way, and particularly if you consider, you know, these often are called like stringy corrections. If you considered 1 over n corrections or quantum corrections, you know, the corrections look like this. And this object doesn't have any nice property under quotienting, right? The log messes that up. So this is really a special property, and that special property is what naturally comes out of these center symmetry type arguments. Any questions about that? All right. Okay. Let's get a little bit more general. So I've been talking about center symmetry and the Iguchi-Kawai mechanism. And as a summary, of course, I showed you can reproduce certain features of the zero-point functions like the free energy density, which implies things about how sparse the spectrum of light states or operators is. It gave you certain properties of correlators, which are very special to holographic theories. And one nice thing is it doesn't really require supersymmetry or conformal symmetry. So this, you can use this to understand certain holographic features of theories of non-conformal branes or other things like that. So you don't, it requires very little. It just requires this higher form symmetry. But if you start cataloging, and this came up a little bit earlier, various examples of holographic theories, you start coming across things that don't seem to have a center symmetry. So if you consider a 6-dimensional 2-0 theory, this theory doesn't have a center symmetry. But instead, it has a two-form symmetry that, were you to compactify the theory, descends to center symmetry. And the bulk dual has all these nice volume-independent properties that I've been talking about. So that suggests that this Iguchi-Kawai story is more general than just center symmetry. You know, it probably extends to higher form symmetries. This hasn't really been, you know, discussed in the Iguchi-Kawai literature at all. But to me, this example just makes clear that the story is a lot more general, and it's about higher form symmetries. The fact that this thing doesn't have a center symmetry or a one-form symmetry is related to the fact that the bulk dual is not a string theory. It's the theory of membranes, which are higher dimensional, so you should expect the higher form symmetry to be relevant in the field theory. In that same sense, you can also consider ABJM at level k equals 1. This is, again, not a theory of strings. Okay? Here it's a little bit more confusing because at general level k, you have something effectively like a zk center symmetry, but at k equals 1, that's nothing. And here, you start seeing that the story is more general than center symmetry. Here, actually, the theory has some hidden one-form symmetry. So this theory is actually mirror dual to Super Yang-Mills, with a fundamental and a adjoint. And that thing has a center symmetry at leading order in n. All I'm ever saying is leading order in n, so that's fine to have the symmetry only leading order in n. But since these symmetries are physical, under the duality, it must map to some sort of one-form symmetry in this theory. So this example shows you that it's not necessarily, even if it's one form, not center symmetry, it's just some generic one-form symmetry, which shouldn't be surprising because associating the one-form symmetry to the gauge group, that step is physical. Okay? Gauge groups can change under duality, so there's no gauge invariant way to associate a symmetry to the gauge group. You just talk about the fact that there's a one-form symmetry and has a certain action on the operators of the theory. That's really the way to phrase it. Okay, we also know to add fundamental matter to certain theories. We like to talk about QCD, of course, want to do this sort of thing. And like I said at the beginning of the talk, if you add fundamental matter, you explicitly break the center symmetry at the Lagrangian level. So you can ask what the hell's going on there. Well, on the bright side, almost always when this is done, and basically any smooth example I know where this is done, you add order n to the 0 amount of fundamental matter. You're in the quenched approximation, so you still have a center symmetry leading order in n. So that's not really a problem. And then there's higher spin duality. So this case is interesting. So this is not a local theory in the bulk. All these nice local features I've been talking about don't come out of the CFT. You know, if you consider the ON vector model, the UN vector model. That theory does not have any sort of center symmetry, not even a leading order in n. It's just a theory of fundamental matter. But that's okay, because the bulk is not a local theory. But you can ask an interesting question, you know, what if you wanted to deform this theory to start looking like a local theory in the bulk, if you wanted something a little bit more stringy? If you take this center symmetry stuff seriously, there's a natural thing you would do to deform the, let's say, the UN vector model. And the natural thing you would do is actually, well, I won't really get too much into the construction, but basically you have the UN vector model. You add, you can add a UN flavor symmetry to this theory, okay? And then you can weakly gauge the UN flavor symmetry. And then you can make your matter from fundamental to now bifundamental under these two gauge groups you have. Now you have a UN cross UN, and you make it bifundamental under those two gauge groups. And that's basically a deformation of this theory that takes you to something that's more ABJM-like, all right? But if you didn't know anything about ABJM and you just said, I want to take this theory and introduce a center symmetry, that's what you would do. And in fact, that's what people did years ago when they would consider theories of fundamental matter and wanted to introduce center symmetry, is exactly that construction. And in the holographic context, this was worked out by Shi Yin and Shiraz Minwala and others who I'm forgetting. And it's really, you know, it's called the ABJ triality. It connects these higher spin theories into more local string-like theories in the bulk, which on the field theory side connects the vector models to the matrix models. So the punchline there is a center symmetry can be a guiding principle to deform non-local looking theories into local looking theories. Okay, so these examples suggest that there's a more general statement than just center symmetry in the Gucci-Kawai mechanism, and it's just that you have some sort of higher form symmetry at leading order in n. That seems to be the more general statement. Now, there are no theorems associated to just generic higher form symmetries and preserving them in volume independence, but okay, that's part of the work in progress. And to come back to something I talked about at the beginning, this sort of helps explain the gauge and gauge gravity duality. One way to understand why gauge theories always appear is that it's very easy to have higher form symmetries come along for the ride when you write down gauge theories. It's not necessary, it's just somehow sociologically as humans, it's just an easy way to write down theories that have these higher form symmetries. But you know, it's totally not necessary. Okay, but it also suggests, I mean, these higher form symmetries imply non-local objects in the bulk, like strings and branes. And so it suggests that these guys are really important in having a theory that has some sort of local limit, some local Einstein gravity like limit. Yeah, so a simple map of the ZN center symmetry is to, you know, shifts of the integral of the 2 form over the string world sheet. So it's really, these symmetries are really associated to non-local things in the bulk. That's the point. Okay, so, yeah. No, it does. I mean, you can take the expectation value of the Wilson surface operator as the order parameter for the transition.
But it's still an S1 without.
Yeah, you can have it wrapped to S1 and then
What do you do
put,
with the other thing?
but just put it on.
I mean, I'm doing S1 and an S5.
Yeah. I mean, yeah, it's not topologically stable on the S5, but you can stick it on the S5.
Yeah, but then it would be 0 right, compared to the S5.
It would be 0. Sorry. Sorry, I understand what you're saying.
So this is a transition which, in terms of confinement, deconfinement, looks like it wants to be
Right.
it's like in the gauge theory, but it doesn't have anything to do with the control.
Huh.
I'm just trying to understand the logic of the statement. I mean, clearly that theory, well, the theory probably has all kinds of higher form symmetries. But
Yeah.
this doesn't seem to be what corresponds with.
Yeah, in that case, in that case, I don't know immediately what would be diagnosing, right, the S1 cross S5 in that transition. Yeah, I don't know. I mean, what I was just saying a moment ago, the fact that's related to non-local objects, that's still true. I mean, the two-form symmetry, as you know, is related to the fact that you have M2 branes in the bulk. But yeah, I hadn't thought about that particular case, actually. That's interesting. Okay, just to summarize the outlook of sort of things going on with various people who I haven't listed. But this sort of topological volume independence I talked about, where you quotient and you get volume independence with respect to quotienting, that is something that is not studied at all in field theory. It's, of course, suggested by gravity and basic field theory arguments, but it would be nice to be able to prove statements about those changes to the field theory directly from the point of view of field theory. Another thing, again, to comment on AdS3 CFT2, there's one assumption that's used a lot in deriving universal features of gravity, and that's that you have, in some vague sense, sparse small OPE coefficients, okay? And the center symmetry stuff makes contact with OPE coefficients because it makes a statement about correlators under space-time quotients. So that's directly a statement about OPE coefficients, so it'd be nice to get some sort of sparseness or some smallness constraint on the OPE coefficients from that idea. And then the other thing which I was just talking about is extend these sort of large N volume independence type arguments to more general higher form symmetries, just stated abstractly in terms of symmetry and the action on operators. And then finally, I have time, but the last thing is, the one example of a theory that I know that comes very close to having nice volume independent properties, but doesn't seem to have any sort of higher form symmetry is the case of D1, D5, but in more particular, just free symmetric orbifolds. These things don't seem to have any sort of center or one-form symmetry. I still think there's something there playing the role of center symmetry and doing the nice things that the Iguchi-Kwai mechanism does. And trying to sort that out is also something going on at the moment. But I'll stop now, and thank you for your attention.
What are you using the Zn for? Because, okay, you always say about whether it's center symmetry or not, but let me put it this way. In the large N limit, this is just a U1, right, that you can think about? Is that?
Almost.
Are you using the fact that it's Zn for something or not?
Sorry, I'm not sure. As opposed
Well, in the
to
large
some
N
other-
limit, are you keeping track of the fact that N is quantized or not?
Yeah, I don't think it matters for these arguments. I don't think. Well, I mean, Zn and U1 are still different at. Zn and U1 are still different even at large N. To be safe, I'll say that it really is a Zn, because in examples where things are done rigorously and proven, it's really a Zn at large N that is used.
Well, typically we know about Zn because there's some Chern-Simons terms, and saying in gravity, right? In the bulk, the typically Chern-Simons terms that keep track of these n's, and they're quantized, and then that's what keeps track of n. Right, for the two forms, right? For the bulk duals of these things are some two forms in the bulk.
Yes.
They have Chern-Simons terms
Yes.
that are quantized,
Yes.
and then that you read
Yes.
n from, these are 1/n corrections,
Yes,
and
yes.
they're quantized.
Yes.
But okay, but modulo that in the large N limit, you don't, anything, everything you said.
The only thing
doesn't seem
I
to-
don't use anything from the bulk in any of this, really. Bulk has some features, and you could understand all this talk as taking a field theory, assuming it has some Zn center symmetry, and at large N, use.
Say I forget where all of this comes from. I forget about gauge theories. You know, I just tell you I have a one-form U1 one-form
If you
symmetry,
forget-
and then I try to see what are the consequences of having a U1 one-form symmetry.
In the gauge theory.
In the theory. I don't
In
want
the theory. Okay.
Say forget gauge. Doesn't matter.
I don't know how to use it in the bulk. I don't
No,
know.
no. In the field theory.
Okay, in the theory.
I don't
I
see
see what you mean.
I
Okay,
don't
not
see
the
you
bulk.
using Zn for anything, but maybe I'm.
Well, the theorem that I was using, the Gucci-Kawai
Yeah.
theorem, really phrases everything as a center symmetry and proves things according to that. Now, I agree.
in the large n limit.
the large n limit.
And you don't care about the 1 over n corrections you said.
No.
So it's not clear how the finiteness of n makes any. The quantization of n. What's the role of the quantization of n?
That's right. Yeah. That doesn't play an immediate role. Yeah, in the theorems and stuff.
These Polyakov loops.
Yeah.
They in principle can pick up continuous phases, right?
Yes,
And they
yes.
transform, so.
Yes. Yeah. Things break at one. This is really just leading an n classical gravity. type
Maybe the question that I'm
statements.
asking is about the 1 over n corrections to this story. I mean.
Yeah. I don't know. I don't know anything interesting it implies there, and there's definitely nothing that exists in the field theory literature that implies any interesting behavior at 1 over n. This mic is really necessary.
So for this, you spoke about this ABJ triality, and you said there is a way to understand this ABJ triality in this framework of yours. So how does this, can you do it also for the lower dimensional case for these higher spin CFT dualities as well, for the coset models?
Oh, that's an interesting question. I would say that if ever you have some theory of fundamental matter, there's a simple way to promote it to a theory that has center symmetry that maintains a lot of the features of the original theory. And it's really this procedure of you add flavor, you weakly gauge it so that the gauge fields don't do too much, and then you make matter bifundamental. Bifundamental is important to preserve the center symmetry because fundamental matter breaks it. That procedure doesn't really care about what dimension you're in. In 3 dimensions is a nice way to, in odd dimensions is a nice way to do it with Chern-Simons gauge fields, which don't add local degrees of freedom, blah, blah, blah. But it's sort of general. Yeah.
So
That
the
answers your
coset
question.
models are somewhat gauged with Witten models already, and but the stringy picture is more that of the symmetric orbifold. So, I mean, both are gauge theories in some sense, but
Yeah. Yeah, I don't have anything useful or concrete to say about just generic theories where you have these higher spins.
Can I just make a comment about the U1 versus Zn? I mean, you can't really be a U1 because the spontaneous rate of U1 is being that it goes from those numbers.
Yeah.
So you can never really think of it as a U1.
Right, yeah. Zn at large n. Yeah, exactly.
There are n distinct phases.
Right, yeah. There's no real conserved current technically, and yeah, that's yeah.
Okay,